Hey guys, Zong here, back with another math video. Our last video was on derangements, so this video we're going to continue on with derangements, and we're going to prove a much easier formula you can use for finding the number of derangements of a certain number. So as we discussed in the last video, and if you haven't watched the video you should watch it, the number of derangements of a number, so like this is the notation, it's sort of like factorial but it's not, is like, say you had like n boys and you had n scarves, I think, and say the boys put all their scarves into a pile and mixed all the scarves up and each randomly took a scarf back. The number of derangements is the number of ways the boys can actually take the scarves back without getting their own scarf. So ways to distribute n things to n people without anyone getting their own thing. And this definition is going to be really important because in order to derive the formula for derangements, we're going to need this definition. You're going to have to really understand and keep in mind what derangements are. So let's try to derive a formula of derangements from n factorial, because n factorial is sort of similar in that n boys and n scarves, and I'm not going to write out the definition because it's like the number of ways you can just distribute the scarves to the boys without having to worry who owns what scarf, and the boys can get their own scarf, it doesn't matter. It's just the total number of ways you can distribute n scarves among n boys. That's what n factorial is. So using these two definitions, I think we can actually come up with a formula for derangements with this. So let's think about this. We're going to use the principle of inclusion-exclusion, or otherwise known as PIE, to come up with a formula for derangements. And if you don't know what the principle of inclusion-exclusion is, I suggest you go watch our video on that. We have a video on that. Essentially, it's sort of like this. If you have these intersecting sets of things like A, B, C, then A intersect B intersect C is equal to A B plus C minus A union B minus A union C minus B union C plus A union B union C. Essentially, the principle of inclusion-exclusion means that whenever you're counting the total number of things in a certain set, and like these sets intersect, and essentially you want to add up the elements of each set, subtract their intersections, and then add the intersections of all three, because when you add these circles together, essentially you're overcounting these intersections. You're like overcounting them. You're counting them twice, for instance. So like after counting this circle and this circle, this area is counted twice. This area is counted twice. This area is counted twice. So you have to subtract these areas, and after you subtract these areas, like what we did here, after you subtract these areas, you've subtracted the middle area twice accidentally. So you've subtracted the middle area one too many times. So you gotta add it back, and that's sort of what the principle of inclusion-exclusion is. If you're sort of confused, I really recommend you go watch our other video on that. But we're going to use that to help us on this question. If I can just, all right. So we have n factorial things, and how do we change from this? How do we get from n factorial to the number of derangements? Well, n factorial is the number of ways n scarves can be distributed among n boys. So in order to get derangements, how about we just have n factorial, but we subtract the number of ways. We subtract the number of combinations in which the boys get their own scarves, in which at least one boy gets his own scarf. Right? That if we use complementary counting and subtract away the number of ways at least one boy gets his own scarf, then we will have the number of derangements from n factorial. Because in derangements, these cases aren't valid. So number of ways one boy gets his own scarf. So we want to do that. So n factorial let's try it this way. So let's say let's just say that we subtract all the arrangements in which each element appears in its each scarf appears in its with its original person. So you have n boys, right? You have n boys. And for each boy, let's say a certain boy gets his own scarf back. So in a set of like 8 boys, boy 1 gets his own scarf back. Then there are 7 factorial ways to arrange the other scarves. So n minus 1 factorial. And this will give you essentially, so if boy 1 gets his scarf back, there are n factorial ways for the other scarves to be arranged, right? And since there are a number of n boys, then that means that this case sort of includes all the this equation sort of includes all the cases in which if a certain boy got his scarf back and the scarves are randomly arranged with the rest of the boys. So, however, this case sort of overcounts the case in which two of the boys get their scarves back, and the rest don't get their scarves back. So let's think about it this way. So for boy number 1, gets scarf back, and there are 7 factorial ways to arrange the rest, right? Boy number 2, let's say boy number 2, we're considering the case where boy number 2 gets his scarf back, and we add on the 7 factorial ways to arrange the rest. Now let's say only these 2 boys get their scarf back. Well, that means we overcounted the case where boy number 1 and boy number 2 got their scarves back twice, because this 7 factorial includes cases where boy 2 got his scarf back, and this 7 factorial includes cases where boy 1 got his scarf back. So if 2 boys each get their scarf back and the rest don't, then we've overcounted this case. We've overcounted this case by a factor of 2. So like this 7 factorial that we counted includes a case where boy 2 got a scarf back, and this 7 factorial includes a case where boy 1 got a scarf back. So in the case where both boy 1 and boy 2 get their scarves back, using this equation, we've overcounted that. So we gotta use principle of inclusion and exclusion, and we gotta compensate for that. And that means that we have to subtract a number of cases where boy 1 and boy 2 get their scarf back. So that would be n choose 2. There are n choose 2 number of ways you can choose 2 boys, multiplied by n minus 2 factorial. Because when boy 1 and boy 2 get their scarves back, there are there are like n minus 2 ways to arrange the rest of the scarves. So to eliminate this overcounting. And now we've overcounted the number of ways in which 3 boys each get their scarves back. Because think about it. Because I want you to think about it like this. Say you have a Venn diagram like this. And this is the number of ways boy 1 gets a scarf back. And this is the number of ways boy 2 gets a scarf back. And this is the number of ways boy 3 gets a scarf back. This is the number of ways in which boy 1 and boy 2 got their scarf back. This is the number of ways in boy 1 and boy 3 got their scarf back. Boy 2 and boy 3 got their scarf back. Just like in principle of inclusion and exclusion. We've added these together with this equation. Now we subtracted these with this equation. We basically added this, we've counted this middle section 3 times, and we subtracted this middle section 3 times. So now we got to add the middle section back again. So now we got to add the number of cases in which all 3 boys we got to add the number of cases in which all 3 boys have their scarves, get their scarves back. And this is how principle of inclusion and exclusion is dealt with. So now we got to add this case back. And using the same logic, we can keep going. So n choose 4, we got to subtract that because now we overcounted. And we gotta keep going until it's either plus or minus. I think it's it's and it's all the way down to n, I think. So it's plus or minus. Depends on how the sequence works out. And yeah, so that's really that's the equation. But this equation's sort of heavy, and I hope you guys remembered it because I'm about to erase it. This equation's sort of heavy to work with, so let's see if we can simplify this a bit. So each term in the equation sort of looks like n factorial minus some n choose k times n minus k factorial. But keep in mind that n choose k is equal to n factorial over n minus k factorial over k factorial. So when you multiply this by n minus k factorial, then we get just n factorial over k factorial. So essentially this equation really becomes n factorial minus for 1 factorial plus n factorial over 2 factorial plus n factorial over 3 factorial. Oops, minus. My mistake. All the way down to plus negative 1 to the n factorial over n factorial, right? So then we can sort of like factor out this stuff, and we can sort of make that. So again, derangements of n is equal to n factorial times 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial dot 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 all the way to negative 1 to the n of 1 over n factorial, which is equal to n factorial k equals 0 to the n of negative 1 to the k of k factorial. That equation is important. That seems like an easy enough equation to use. Oh, but believe it or not, we can get this down even easier. So this is a long journey. So we have to keep in mind, actually, we have to notice something here. It's sort of a black box step, as my math teacher would call it. It's sort of a step that you don't really know, but you guys remember how this is just something you should you should know from sequences in series. I'm not going to prove it right now; it would take too much time. But e to the x is equal to the limit of n to infinity of x to the k over k factorial. And oh, sorry, I made a mistake there. Is equal to k equals 0 to infinity of x over k to the k factorial. And so e to the negative 1, or 1 over e, is equal to negative 1 to the k over k factorial. You know, that looks sort of familiar. That looks really familiar. That sort of looks like that. So is it possible we can just replace this with this? Well, not completely. Remember, this only goes up to n. This goes to infinity. So if we replace this portion of the equation with this, it's going to be an approximation. But let's say we do. Derangements of n is equal to n factorial times 1 over e. So it's just n factorial over e. Again, this is an approximation, but how accurate is it? Well, we have a table here. It's like it sort of compares the different approximations, and it's pretty amazing. Here's n, here's the number of actual derangements, and here's the formula with rounding. And it's completely accurate if you round it for n equals 1 and above. I think it's pretty incredible. So the easy formula for finding derangements is just n factorial over e for 1 and above, and you have to round. So I think that's pretty amazing, and that's basically the proof of the formula.